So we're back with the next episode. And if you were looking at the comment section in the previous episode, someone asked some really good questions, about the maximal compact subgroup and also about continuous representations or locally constant representations. And they said, they asked something to the effect of, if we're looking at a represent, if sort of the continuous ones, representations that show up over here, just happen to be locally constant. Well, isn't that going to happen for representations as well? Something like that? And doesn't that, shouldn't there be, how do other interesting representations show up? And actually, that's exactly the things that we're going to study. So surprisingly, you might think, oh, locally constant's pretty boring. Yes, I mean, in some sense. But so let me just start right off. Let's jump right into this video with a definition. So we say that a representation, pi v, so not necessarily finite dimensional, this is key, is smooth. And so, for now, I always just mean GLN of QP specifically. So we say that it's smooth if for all vectors in here, there exists, oh geez, sorry, we say it's smooth if the stabilizer, so if all the G in G such that pi G of V is open. Right? So well, how is that related to locally constant? Well, you can sort of see, right? If you look, if you take the pre-image of any vector, it's going to be its pre-image is an open set, right? So somehow our representation is like a bunch of locally constant functions, right? Like you just sum over for like all these vectors, these locally constant functions. And so these are actually the representations that we're going to study, are the smooth representations. And in some sense, these are the right ones. These are the ones that we want to look at. Maybe I will be able to, I'll give more of a justification for that later as to why that's the case. For now, I don't want to say anything too fancy to like scare people off, or maybe it excites you. I don't know. Different people feel different ways about these things, right? But um, another way to look at it is gosh, no, I'm not going to say anything about it right now. It's just this ends up being the right idea. This is the thing that we want to use. And there's advantages and disadvantages to this, right? Like in some sense, it's maybe a disappointment or a letdown. It's not like the most interesting kind of continuous thing, right? But on the other hand, it's going to save us some headaches. For instance, like calculus or the measure theory that we're going to be using becomes really nice. Like integrals become finite sums because of conditions like smoothness. And that's going to be important. It maybe later today, probably not. We're going to talk about Hecke algebras, which are just some other way of discussing representations that are really useful and important. And it turns out it's like we literally try and integrate stuff to do with these representations. And it's just a lot easier when everything's a finite sum, right? But it's still interesting. I think you'll find it still interesting. The other thing that we need is the notion of admissibility. So we say that a representation is admissible if for all, now let me see, I have my notes open here. It's all right, open. It doesn't need to be compact. So for all open, I sometimes like to use, a subset symbol with an O to mean open subset. For all open subsets, the set of vectors that is fixed by U, so this is all V in our V. This is still for a representation such that, pi G of V is V for all G and U. We want this to be finite dimensional, right? So we're allowing the possibility that our representation is infinite dimensional, but sort of it's got these little finite dimensional pieces to it. And why do we want this? Again, maybe this is something that becomes clearer over time, but you can sort of think about it like, presumably if you're watching this video after the first one and following along, presumably, and don't worry if you haven't, but I'm guessing you've seen some module theory before, right? You've seen, we have a ring and we have the category of R modules, right? So R modules with a big M. And this means that we allow those modules to even have like infinite rank, right? Like these infinitely generated things. But of course, so I'm just playing with the volume levels a bit. Of course, that can be sort of unwieldy. And also the things that come up in nature, um, sometimes they're not that, right? Like sometimes it's sufficient to just consider the finite dimensional module. Sometimes that's all we're interested in, sometimes it's all we need, sometimes it's all we can understand. And so admissibility is kind of like that. It's kind of like a finitely generated condition. So okay, I'm probably philosophizing way too much about that. So the other thing I want to talk about is the one-dimensional. Let's start, right? So what are representations? Well, if you've again, you've probably seen some representation theory if you're watching this. So uh the most obvious, representation, our favorite, oop, that should be QP, uh, is just the trivial representation, right? So we just have right, this is GL of the complex numbers. We just send every matrix to the number one. Right, trivial representation. It's irreducible. We love our irreducible representations. Fantastic, right? So clearly this is smooth. I mean, so inherently our finite dimensional representations are going to be admissible. Great. And it's smooth as well. I mean, let's just go up and look at our condition, right? We need the stabilizers to be open while the whole thing is the stabilizer, right? And of course, G is open in G. So we're done. Great. So probably, I mean, as a first pass for believability, if our definition's good, we're trying to keep meaningful representations. Okay, maybe the trivial representation isn't so interesting, but like it's also pretty damn important, right? So this is a one-dimensional representation. What other one-dimensional representations that we have do we have? Well, it turns out that actually for GLN-QP, all of the one-dimensional representations are of the form. Well, okay, let me give you one other one first before I reveal that. So much like, of course, any matrix group, how do we get down to here? Well, we have our determinant map, right? This is a very famous homomorphism from these multiplicative groups, right? So I can take G and I can send it to the determinant of G. But then we want to get a complex number out of this, right? We're trying to do complex representation theory. So, well, how would I do that? Well, this is a single p-adic number. I could take my p-adic valuation, right? So I'm not going to write the little subscript p because everything here is inherently p-adic, right? And sometimes we write this character as new. So this whole thing we write as new. And then you might also get the idea, well, what if I want to, uh, really I use the determinant, and then what about the other characters that exist here? And so there's two kinds that we're going to care about. I won't get into details now, but there's ramified and unramified. And maybe should I talk about them now? I don't see why not. It's not that crazy. Sure. I'm not doing the series with any plan at all. A vague plan in my head. I'm just shooting from the hip, so to speak. So all of our unramified characters are exactly of this form. So they're new to the S, where S is a complex number. So that is, it takes some p-adic number and evaluates it using the p-adic absolute value, and then puts it to the power of S. So these are all of the unramified representations from QP cross to C cross. And notice that these will be equivalent, right? If I take X and S plus 2 pi I, right? Those will be equivalent. So I actually get like a, complex numbers minus modulo 2 pi I Z. I get like a torus of unramified representations. The next part I could be a little bit wrong on. In fact, in my this question came up in my candidacy, and I sort of got there to the answer was guided there, and then, but yeah, I think the ramified one. So the part, so unramified means that these are another way to see it is that these are characters that are trivial on ZP, right? Because one of the equivalent definitions of ZP is that it's exactly those p-adic numbers whose absolute value is at most one. So we saw this, or I mentioned this in the comment to one of the viewers, if you're looking at the comments in the last video. Great. So that means the ramified ones, that means our ramified, um, those are going to be non-trivial on ZP, right? And so in particular, let's try and find a non-trivial map from ZP into, or I guess ZP cross is what we want, into C cross. And now we are trying to find, well, basically we're trying to understand this map by understanding what sort of kernels can exist, right? So this has to be a non-trivial ring homomorphism. And the image in here, is it going to be... see, now I'm doing things live and off the cuff, and and I'm I'm forgetting. So I know if we look here, the point is that so remember we have a unique maximal a unique maximal ideal in this ring. And I believe the conclusion from this argument, that let's call it a proof sketch, is that basically for each power of the prime ideal modding up by this prime ideal, those are exactly our ramified characters. We're not actually, I don't know why I even tried going into this tangent that I clearly didn't prepare for well, because, well, we're mostly going to be talking about the unramified characters anyways. That's what's going to play the important role here. So let me give you one example of an unramified character that's going to be really, really important for us. So that is, how should I write it? Well, do I want to talk about that one quite yet? No, we're gonna save that for a video. And let me just say this. So let's go back. So we're trying to understand what are the one-dimensional, right, irreducible representations of this matrix group. Well, we know we can use the determinant character together, with these other characters of the multiplicative group of the p-adic numbers. So it turns out that all the characters, at least the smooth admissible ones, but I think probably just all of them, like algebraically, are of the form just chi of the determinant for some chi, which is, a character. So sometimes this x upper star of G means the characters of G. Well, actually, that could be some sort of algebraic thing. I don't want to. It's just this where chi is a character. And the point is that we have two kinds, ramified and unramified, and we have pretty explicit descriptions of both. And it turns out that actually for GLN, all irreducible, finite dimensional representations are of this form. So this is exactly all of them. Just taking a determinant of G and then applying this character. And that's kind of surprising, right? At least if you've studied, the representation theory of, say, complex Lie groups or something, there's many, many finite dimensional representations, and we can combine them and all, there's these interesting combinatorics of how you take tensor products and stuff to like form higher dimensional irreducible representations and this nice classification. You know, like SLN has these symmetric power representations. But for the p-adic groups, at least all of our smooth, irreducible, finite dimensional representations are of this form. So interesting. That means that in order to get at the more interesting representations of these groups, we're going to need to study some infinite dimensional representations. Oh, by the way, there's one comment. I think maybe that's where I'll leave it for today, but there's one comment I wanted to make going back to his question about, we want our representations to be locally constant, to be made out of locally constant maps, basically. There is another approach to this that one of the professors here, told me about, in which you try to do some sort of functional analysis, and because, well, in the case when V is infinite, right? Then, well, this isn't like a nice thing. Like, what's the topology, right? When V is finite, this is just GLNC, right? And then it's easy, and the topology is just inherited from C to the n squared. When V is infinite, though, now we're doing functional analysis, and we need to talk about like these operator topologies and stuff. Maybe if I'm feeling motivated, I'll find the reference for you next time. But there is an important and interesting discussion to be had about like what topology do you put on here, and there's some comparisons of different like operator topologies. I'm probably going off into the deep end, so if these words are not your vibe, don't worry. We're not gonna dig into the stuff, but just thought I'd mention that, yeah, there's some operator theory stuff, and then it turns out like once you pick the right um definition from the operator topology and you ask that these maps are continuous, it still just comes out to this locally constant thing. It just turns out to be smooth, as I defined above. So we could ignore all of that functional analysis. But there's interesting considerations there, that are maybe worth looking at some point. So that basically wraps it up for now. So that is we've understood all of the irreducible finite dimensional representations of p-adic GLN. Oh, that was pretty easy. But now we're going to need to dive more into the structure of GLN itself in order to come up with some more interesting representations. So stay tuned for that. Thanks for joining me, and I'll see you, I don't know, in a day, maybe two.